folks. It's fully Gupta. Today, I'm going to talk about adaptive power calculation for low power operated chips. In today's scenario, when we look at our life, we are using lot of systems or devices which are remotely operated and has become essential part of our life. Thus, it becomes very necessary to mix those power lines longer on battery. You don't need to charge again and again. And whenever you need, the battery is available to support an adequate current. How we can make sure that's happening? We can design system, we can design the chip with the correct specification so that we can deploy the battery which can adequate current whenever it is needed. A proper calculation is required when we are designing the system, we are designing the chip or any other part of this overall device we will be using in our day-to-day. Some of the examples of these devices, smartphones, we use day-to-day life. We want to charge it for a small time, we want to use it for a longer time. Tablets on cars, many more things. So let's just go through this presentation and see what are the components which are responsible for power, what is the current state of power, how we are calculating nowadays, what are the problems, flaws in our current methodology and flows right now during the power calculation for the chips, and how it impacts the overall process. First slide. So power calculation challenge. What are the challenges which makes this process a little bit difficult? It's the inaccuracies when we calculate the power. So there are a lot of parameters what we need for power calculations are dynamically changing in day-to-day chip design process, or they keep changing as chip process progresses. So if we look at any holistic chip design process, we can divide it into multiple subportions. Architecture, we have RTL, and we have physical design, and then we have finals. These parameters can be based on the formula, the toggling file, the load capacitance. Sometimes we look at the frequency and voltage variation level also. So all these parameters are dynamically changing. And when we try to calculate those things, if those are changing, estimate for the power may not accurate. Early inaccuracies are the another set of components. Like when we started with one of the architecture, we did not consider few features, and those features we are adding at the later stage, and those are some high frequency switching features that may change power computation, and it can cascade with many other things in the latest. The distributed network issues also comes in the picture. We calculated the power, some numbers, and then we designed the power net, and we are using it. A lot of things has been changed in terms of, we added the feature, changed the RTL that increased the area of the design. When we need more current, we need to make the power network robust, and that will add the load capacitance. So the total power. These are some of the challenges what we are seeing in day-to-day chip design process. Current state is the fixed calculation. How we are doing it, we have some specification based on the architecture. We are looking into it. Say we are doing CPU designs. Fetch will be happening in this cycle. So this logic, in this particular cycle, for 2 cycles, this amount of logic off, only leakage will be there, and so on. So we have this kind of scenario, but actually we cannot cumulatively look at entire design switching, that how this will be switching. So the possibility that we are still leaving a significant margin of errors. using static design parameters. Like, okay, we will be having this much area, the area will grow by this much. And this is how it is going to change our load curve stance. But there is a possibility that when we are going through the design closure phase, these parameters may change. And if we will not include, we may see that the calculations what we have done for the power may be inaccurate or sometimes what we see that during the late stage when we are done with all these things, we figure out, okay, now whatever the power we were estimating has changed. The reason may be during area convergence, what designer did, he did use a lot of EL leaky cells, ELVT or ELVT cells, which reduce the area but actually increase the power. And all these things mix and match will result in a suboptimal designs where it can have higher power consumption, it can have lower performance, and at the same time, the battery may be leaking really. So all these things are in the current state of the chip design. How we can overcome of all these things? So we know that we are starting the design, we have some architecture, but can we account for extra feature if we know about, okay, can we model some kind of additional margins when we are computing it on the power initially? So actual toggling file based on the design requirement we get at the end, physical design closure when we run gate level simulation. But can we model these kind of FSTVs in the starting so that we can calculate the power in a more way? So the calculation can be done based on the comprehensive power estimate and using preliminary specification. Also, we can use some statistical models based on prior experience, prior design experience, prior technology experience, and based on what we are thinking that this feature will be adding or something. Now, at the same time, we can dynamically incorporate these real-time measurements data and can refine parameters. So at the architecture level, we estimated, okay, this much switching activity will be. But when we are moving for, we are not able to do enough clock gating. Can we change that kind of parameters and can do the recomputation? Adjusting those power specification and then enhancing the precision of those power computation will help us to optimize the battery. And then after that, we can those results at the same time by benchmarking against whatever the test vectors we have to see whatever the improvements we have done actually going to meet the power requirement or not, or still we need to provide the feedback to the architecture or to the RTL team or to the physical design team that we are not meeting. And we can take this adaptive methodology and can go through a couple of different cycles to close it. Now, key milestone for adaptive recalculation. So as I mentioned, based on the architecture definition, that is the baseline power budgets where we have a specification and we can use statistical modeling. We can do this through the RTL development. So when we know that this is the RTL, this is the activity will be there, we can do some simulation at that time and can do all the analysis for the power based on the workload analysis and available RTL. Next is the physical design. When design is placed off, clock tree synthesis is done, routing is done, we have more realistic value of load capacitance. We can have a good quality of toggle rate file, and we can do much more accurate power profiling at physical design stage. Pre-silicon validation, when our design is ready to tape out, ready to go to for mass generation to the foundry, at that time, what kind of power calculations are there? So we can do power computation based on whatever FSTV we have. We can have functional FSTVs, we can have DFT-based FSTV, and in those two scenarios also, there can be multiple modes. So for each and every mode, whatever we were expecting, are we meeting those goals? No. So we can check. Now, tracking input quality at each and every stage, as I mentioned, when initially we are starting the design, we can account for some of the factors, toggling date, okay, that all the sequential and all the input outputs should have at least 45% activity annotated. The parasitic data can be assumed to be 80% based on the model, 20% based on the real one. Same can be scaled going further. So during the synthesis stage, we can consider, okay, 65% toggle rate should meet. Parasitic data can be little bit more accurate beyond the 55 or more percentage because we have physical aware synthesis capabilities available. Place and route, we expect 80 to 100%, or I'll say in ballpark favor between 95 to 100% toggle rate to meet. And then the completeness of parasitic should be 85 to 100%. And then we can calculate a more accurate power. And then like here, the numbers are a little less because we are not considering the optimization. So we can calculate these numbers at the just before, at the starting of the place and route, and at the end of the place and route, and the final. And so that's where the 95% to 100% comes, and 80%. When we have these kind of collaterals available, we can include few things based on the statistical models, and few inputs are the actual, and we can have a very much approximated power calculation. Automation strategy. So internally, we can make our methodologies or process in such a way that we can intelligently identify available input parameters. So like flow, if this file exists, like FSTM file exists, use it. Otherwise, use a pessimistic toggle rate. Implementation implementation of optimal calculation models based on the data maturity. So how we will be going further, whatever the data maturity will be there, based on that, we can refine our models. And proactively, we can flag, okay, FSDB is missing, this library is missing, the toggle rate looks really low. All these things we can flag and can report it to the actual owner. If it need to be feedback to the RTL, or if need to feedback to the architecture, or if need to be feedback to the physical engineering. Wherever there is a gap of something missing, we can bridge with the help of predictive models. So let us say if initially DFT FSTV is missing, can we generate some kind of model which can predict the activity, and those can be leveraged in these computations. Any historical data can also be included, and self-prediction also available if we can utilize AI. At the same time, when we are doing all these computation, we can provide a feedback to all the cross-team members. We can work with the design verification team. Okay, this is what we are seeing. This is what we should see. Where is the mismatch? And can look at all these industry standard tools to make sure that whatever the power analysis we have is accurate. Kind of dashboard also we created, which can be shared across all the teams, and they can look at the same time, take the proactive action, whatever is required. So power distribution network optimization is also part of it. So based on the initial computation, we designed some kind of power network. So we need to precisely calibrate to match the dynamic power requirements so that we can provide the adequate current to all the circuits at the required frequency and voltage. We need to make sure that we do not have any IR drop issues. We do not have any electromigration. We need to have a good network which can supply adequate current. At the same time, we need to make sure that we are leaving enough routing resources for the clocks and for the signal routing, so that we will not run into the crunch or congestion situation. And that overall, we will see that we have enough power getting done. When there is a certain amount of logic doesn't need to switch, we have power getting done available. Or any kind of operation which can provide more battery dynamic voltage and frequency scaling. At the same time, let us say we can reduce the frequency, reduce the voltage, and can perform that operation slow. Or a kind of camera example, when we are not using it, the tool or the system should automatically switch. So those kind of optimization can be done to get better battery. So when we use these kind of techniques in real life, we see that we can save 30% to 30 to 40%, or in my case, I have seen 37% power saving during the chip operation. We saw that when we calculated the accurate power and designed our network, we were able to improve efficiency in terms of performance by 42% without any area penalty, and battery longevity improved by 2.8 times. All these things coming from one of the battery operated devices running at very high frequency. Implementation roadmap, as I mentioned, that all these statistical models or static models, learning based on the prior designs, can be integrated in the tools and methodology and flow. The team of the engineers, all the way from architecture to RTL and implementation, can be trained on the adaptive power calculation methodologies so that they can look at each and everything very carefully and can provide the right input, or they can do the right job. Or for a physical design engineer, if they are looking at more power in their reports, they can analyze and debug why the power is more. Are they using the right toggling, or they forward to open the leaky cells, or something else? Updates. At the same time, when we are implementing these kind of methodologies, we need to have a checkpoints which automatically triggers the power calculation and tells us. So in the flow itself, when we are running synthesis, we need to write all the power reports. When we are running place out, it should write power report after the clock out and after the routing. So when we are tracking it through various phases, we can see the difference and we can easily identify the root cause if there is any differences. Systematically, we can refine these prediction models or FSTVs or any other required input for the computation, and that always helps to have more accurate power. So key takeaways from here, we are doing adaptive methodologies versus the static. We have more accurate power computation at each and every stage, and we can collaborate with the right team to provide the feedback so that they can enhance their process to provide better inputs to the next stage. Like I have seen that I have 4 cores which are switching simultaneously at the same time and consuming a lot of power. I provide this feedback to the architecture team, and they came up with a solution. Okay, let's not turn on all the core at the same time. We will turn on the cores based on the load requirement so that we are not drawing the power at the same. And if there is a need of all 4 cores switching at the same time, we can distribute the load so that when we distribute the load in such a way that based on the clock skew, all the switching will not be happening at the same time. Driven approach is always good for any kind of methodology and process in engineering. When we have comprehensive input quality tracking, what kind of qualities is this going to give us the correct computation, or anything else is missing? What kind of margins we can have to avoid errors? So all these calculations based on the data can assure that we have the right automation. Of course, when we have AI and ML available today, we can fetch a lot of data. We can model missing gaps and can utilize day-to-day process. And also at the same time, these can be easily integrated in the EDA flows and can provide accuracies to our implementation and other methodologies. Also, it makes really fast when we are doing these calculations using AI and machine learning, though there is a cost function of actually cost as well as runtime and high computation. And so this one from my side for today's reach out to me if you have any question. Thank you very much. Have a great day.